a la siguiente charla. La siguiente charla, que es una ponencia de la profesora Carol Mudel. Es un Impact Talk y el nombre es Universal Frontiers, the Imperative for the New Leadership, Talent and Innovation in Space. La ponente es la profesora Carol Mundell, Director of Science European de la Agencia Espacial Europea, de la European Space Agency. Professor Carol Mundell is Director of Science at the European Space Agency and Head of the European Space Astronomy Center, Madrid, an award-winning astrophysics innovator and science diplomat. Mundell served no sé si Mandel or Mundell, Mandel, excuse me. Mandel served as a UK government's first chief international science envoy and was the first woman president of the UK Science Council. She holds honorary fellowships of the Institute of Physics and the British Science Association, won the 2023 Fred Hoyle Medal and Prize, and was named FDM Every Woman in Technology Woman of the Year 2016. Thank you, Carol. Thank you for
Muchísimas gracias. It's a great pleasure to be here this afternoon. I know you've all had a very long day, and so what I'd like to do is give you a whirlwind tour of the universe. But what I would also like to do is explain a little bit about how the European Space Agency works. And I became director at ESA just 1.5 years ago, and it's been an incredible job that I'm very privileged to hold at the moment. As you've heard, I'm an astrophysicist by background, so I began my career as a research scientist, as a professor ultimately, and head of the physics department in a major university. But I was seconded into government in 2018, where I served both as the chief scientific advisor to the foreign ministry and also ultimately the chief international science envoy to the government. And what I saw in that role was the power and the power of friendship and international collaboration as a force for good in the world. And I think really space epitomizes that for me. Scientists compete, we're competing for the best ideas, we all want to win a Nobel Prize, but we also have to collaborate because we cannot work alone. And many of these big technology programs now are too big for one country. And really that's what the European Space Agency does. It brings 22 countries together to collaborate for peaceful uses of outer space. And the way we work, as I say, we have 22 countries. We were founded 50 years ago with just 11 countries. And there are 22 countries across Europe, including the UK. And each of those member states pay a subscription into ESA, and they all have equal voice. Spain is a founding member of the European Space Agency. And last 2 years ago, in 2022, the ministers of all of those 22 countries came together, listened to my Director General, Dr. Joseph Ashbacher, who's in the middle of the photo there, and he put the proposal on the table as to what budgets we would need to satisfy the ambitions of all of these countries together in the coming 3 years and look into the future. So it was a very successful ministerial. We had a very good budget, and all the ministers agreed, whatever their political flavors were, whatever the challenges were they had in their own countries, they came together in this very inspiring way and decided to invest in space. And really these were the values and visions and shared themes. So fundamental to everything we do is world-class science. And as the Director of Science, it's my responsibility to help our communities, our scientists across all of the universities in our member states and our research institutes, our governments, our industries to deliver world-class science. And when we do that across Europe, we are then partners of choice for agencies like NASA and the Japanese Space Agency. We, of course, need technological innovation because we're always asking big questions about the cosmos, and in order to answer them, we actually drive innovation, the discovery and the creation of new technologies. And you'll see in a moment some of the extreme places in the cosmos that we have to make our space technologies work. And ultimately, when you're able to solve these big technological challenges out in deep space, it's then amazing what you can achieve here back on Earth. Commercial growth is also important because obviously we don't do this just for the fun and enjoyment of it. We do it so that we can have a positive feedback to our economies. And if we have that commercial growth, it also means that our companies compete with one another to win these public contracts. And those businesses are then competitive beyond Europe. And so you get, again, this positive economic cycle as well as technological innovation and that world-class science. And pulling all of this together, of course, we have one planet, home Earth, and we care very much about the sustainability of our home planet. And much as we study planets elsewhere in the cosmos, we haven't found anywhere as nice to live yet as Earth. And so sustainability is very much at the heart of what we do, both in terms of the programs that we have where we look down on the Earth, and we might study water or methane, we might help governments with forest fires or floods, but also how we behave in space. And so as an agency, we have a thing called the Zero Debris Charter, and we promise that any mission we launch, we will make sure we clean up at the end of the mission and we bring it back home safely, and we don't leave it to become future space junk for future generations. We also had a bit of a crisis last year where we were between launches, and so we didn't have access to space. And it's very clear in today's uncertain geopolitical times, we have a war on the edge of Europe, that we need unique access to space. We need to have our own European capability. If we want to be space players, we have to be in space. I can't do space science if I'm not up there. And so we are very happy that we had our maiden Ariane 6 flight in June, July, and so we're back in space. So this is very exciting. And really, for me, last but definitely not least, is inspiration. And what you will see from the missions that I give you a taste of today is that these are long-term missions. These are generational. So there are many engineers who I meet who will say, well, when I was a young engineer or when I had just graduated, I worked on this program and now you've launched it. So it's always inspiring. And I meet people from all walks of life who say, I had a part to play in that mission. And sometimes they're very emotional about it. I've got goosebumps just thinking about it now. So the ESA science program really is the backbone of the agency. 50 years ago next year, we were founded between the merger of the European Launcher Organization and the European Space Research Organization. So it was really a vehicle to go into space and something worth launching, to say it simply. And since then, we've evolved an incredibly rich and diverse science program. And you can see here just a few of the key topics that our missions cover, everything from near-Earth heliophysics right out to studying the nature of space-time. And I'll give you a flavor of those as we work through the missions. We have a range of mission sizes from our very big flagship missions that might take 10 to 15 years to develop, through to our medium class and our small and fast class missions, which really help new countries learn how to do competitive space missions. International collaboration is also important. We work closely with our colleagues at agencies like NASA. And we also have a really innovative technology development program because all of our member states provide the instruments that go on the spacecraft. So you might be in a science institute where one of your professors might be developing an instrument to fly on one of these iconic missions. And I also wanted to put in a comment about ESA in Spain, because as I say, ESA was one of the founding countries, Spain was one of the founding countries of ESA, and we have this incredible site just about 30 minutes drive from here. I have the privilege not only of being the Director of Science for ESA, but also the head of the European Space Astronomy Centre, which is just, as I say, 30, 40 minutes drive down the road. It's a hidden gem, it's in a natural park, and it's a very special place. And we have 500 scientists and engineers who work at ESAC. And we are very much a global hub for scientists and engineers to come and talk and work together and come for conferences. And we're also looking how we will support Portugal and Spain in terms of being a gateway really for the Hispano-America, Latin America, the global south, up through into Northern Europe. Paris is our diplomatic headquarters, but for me, ESAC in Spain is the heart of a different centre, which we have ambition to develop further. And this really is the home of science. So originally it was a tracking station, so we had a radio telescope there, and it was a nice radio quiet place, which is why it's out of the city. And the tracking station was there to track the satellites and bring the data back. But the Spanish government decided some years ago that they really wanted to establish a proper European heart of space in Spain, and they decided that this beautiful location was the place to really invest. And what they wanted to do was make it the heart of science. So science is everywhere, everybody does science, but ESAC really is the home of space science in Europe. Now, I've talked about 50 years, and 50 years ago when the agency was first formed, we were learning how to do space. 50 years is not very long. 2004, there was this iconic mission, and this was the NASA Cassini-Huygens mission. So at this point, the agency, ESA couldn't do its own mission, but we took a piggyback ride with Cassini. And this is a movie of our probe, Huygens, landing on Titan, which is a moon of Saturn. This is still the most distant probe ever that humanity has landed on another body in the solar system. That was 20 years ago we did that. That was 10 to 15 years in the development. And the spacecraft landed softly and safely, and you can see some of the stills there, right down in the bottom right-hand side. It looks like a riverbed with boulders, but they're actually frozen blocks of methane. We weren't sure what the surface would have. We couldn't fly a reconnaissance vehicle. We just had to drop our probe and hope for the best. We expected there to be methane lakes, so the thing had to float. But actually everything's so cold it was frozen. And you'll see in a minute that we plan to go back to Saturn and do something more ambitious. But that was 20 years ago this year. That is an incredible achievement for European space scientists and engineers. But as I say, we were not mature enough yet to do our own major mission. 10 years ago brought the iconic Rosetta mission, which you may remember, you may have read about, you may have watched. Again, that movie's not artificial intelligence. It's actually the movie of the probe landing on the comet. This is a comet. So Europe landed on a comet. Now, that's very hard. Comets are not massive enough to have a natural gravitational pull. So not only do you have to fly out and chase the comet, you also have to fly around the comet. So your flight dynamics is very complicated. So we have wonderful engineers who know how to do this. There isn't enough gravity to hold your spacecraft in orbit, so you have to do that yourself. So all of this mission, flying out there, waking the spacecraft up, hoping that after that long journey to the comet, the spacecraft would still be operating, and it was. And then the little Philae lander landed and took these incredible photographs, and there's still science coming out today. 10 years on, we're just celebrating the 10th anniversary of this incredible mission. So all of these technological innovations really develop the future for us. And what I want you to think about is, what might your future be? What great questions would you want to ask that you might be part of answering? We've also been orbiting Mars for 20 years. This is our Mars Express mission. We've made many discoveries. We've measured the depth, the deep water, the frozen water, the surface water. There's a dynamic water system across the whole of Mars. This is Olympus Mons. It's the tallest volcano in the solar system. So you can imagine this is big. And most recently, we actually found that frost forms on a daily basis on the top of this volcano. And again, this is the beauty of having missions that last for many, many years. You start to learn more and more. So we do need to launch new missions, but we also need to make sure that those missions are built so well that they can continue to do new science when new generations come along and say, I think I could use this for something different. And that's the frost on the top of this volcano, which is rather incredible. We've also been mapping the surface of one of Mars's moons, Phobos, and this is to help our Japanese colleagues who in 2026 want to land on Phobos. And we thought, well, it would be better to use our satellite to map Phobos to help them find a good landing site rather than them having to guess the way we had to with Huygens. And what we think we've discovered actually is that maybe Phobos and Deimos are not moons. They might actually be the remnants of Jovian comets, very much like the comet that Rosetta's Philae landed on. So we're all constantly learning new things about the solar system and transforming what we think we understand about the cosmos. So overall, as I say, we've been operating now for nearly 50 years. In the bottom row are the missions that we've developed in the past, which are now no longer in operation, but we have all of those data available in our archives, and you can go freely and use those data. On the left-hand side are our solar system explorers, and on the right-hand side are the satellites that we use to explore the entire electromagnetic spectrum. And really, light is the tool that we use to probe the physics of the cosmos. We can't fly to a distant galaxy, bring a sample back. We actually have to use the light, understand the laws of physics, to decode the physics of these distant phenomena. The missions in the middle are the ones that are flying at the moment and delivering data to us as we speak. and the ones at the top are the ones that we're building and we have in development that will fly in the future. And as I said, these are long-term missions. So along the bottom, you can see the date, and you can see this beautiful list of missions that cover everything you can think of in science. Green are the ones that are operating, the blue ones are in legacy, and the pink ones are in development. And if you look at the bottom, the longest line there is the Hubble Space Telescope. We were partners with NASA for Hubble, and it celebrates its 43rd, 44th anniversary this year. And we're continuing to innovate and put new instruments on there in recent servicing missions. And really that is now underpinning many of the observations that we're now making with the James Webb Space Telescope, which of course is its successor. But over the next 13 years, the European Space Agency will launch a major space science mission every 1.5 years. So you can imagine the science that's going to start to open up. You can imagine the incredible data sets that are going to be coming, that will be there for the next generation to start to mine and ask new questions, as well as to deliver to the core reasons for the mission. Now, as I say, I took up post in 2023, and within 3 weeks, I had the privilege of going out to French Guiana, to Kourou, to our launch site there, for my very first ever rocket launch. Oh, you can't describe. Hands up anybody who's been to a rocket launch. Oh, we have one taker. They are incredible, yeah? I mean, nothing like it. I didn't know what to expect. I was meeting my team for the first time. They'd been out there for 3 months getting this ready. This was our very first L-class mission. This is, 1.4 billion euros worth. This is 20 years of people's lives. You've got to get this right. It was the penultimate mission launch from the Ariane 5 rocket, which had done a beautiful job on the James Webb Space Telescope. Now, I'll explain in a minute why we had such a tiny launch window, but we had 1 second to launch at a particular time each day. And we took our VIPs, we did the first launch. 5 minutes before countdown got to 0, the launch was scrubbed because of weather. And that's the point when you stop being just excited and you start to be a little bit terrified. And that was the moment when we all said, oh, wow, space is hard. So our teams continued to work through the night. The rain lashed against the windows. The local fire brigade came out with their axes and hacked off the ice from the freezing fuel line. So a real team effort. And then the next day we launched with just that 1 second launch window, which was absolutely incredible. And then our 85 square meters of solar panels, the world's largest solar panel array, unfolded and the spacecraft powered itself and is on its way to Jupiter. We have a suite of 10 instruments from scientists from across Europe, and they will measure all sorts of properties of the Jovian system. And we're going to use Jupiter and its moons really as a mini solar system to try to understand our solar system. We can't study ourselves because we're in the system, but we can study Jupiter as a mini solar system. And the big question we really want to answer is whether the moons of Jupiter could be habitable for life. Obviously, that's one of the fundamental questions that humanity asks. Are we alone? I think it's profound if we discover that we're not alone. It's equally profound if we discover we are. And the first step to that is looking for the signs of habitability. And we think that life originated on Earth from the salty oceans, and we think that these frozen moons beneath the icy crusts are vast liquid oceans, salty liquid oceans. And in those oceans, that could be a condition where life could emerge. And so what we'll do is we will go out, and I'll show you in a minute the tour of the Jovian system. But not only are we interested in Jupiter and its moons, but we're also using this mission to teach us about other Jupiters in the world. We're now finding tens and hundreds and thousands of Jupiters in the cosmos. So again, that asks, a bigger question about the prevalence of life in the universe. Looking for habitable worlds beyond our solar system, again, starts to give us a sense of scale and maybe how special we are or how special we're not. The Jovian system is also very extreme, very high magnetic fields, vast accelerations of particles, intense radiation fields. So our astrophysicists are also interested in this planetary mission to study some physics. So this was a beautiful launch. I did stand in that tunnel where the black smoke's coming out, 1200 degrees Celsius when there's a launch. I didn't stand in it during the launch. It would be toast. Any of you followed this online at the launch? Anybody see the sloth? Didn't see the sloth? There's a little sloth. Everybody worried whether the sloth had been toasted. We didn't toast the sloth. We rescued the sloth. These are some JUICE selfies. So this is a camera onboard JUICE looking back at Earth. So this is beautiful. It was really good for public engagement, particularly for young school children. This is a view of our home planet from our Jupiter mission as it goes out. But it was also very important for our engineers because not everything always goes according to plan. And the launch was wonderful, and as we started to commission our instruments, we realized that this rime antenna, which is a bit like a folded up fishing rod, needed to spring out so that it could make its measurements when it gets to Jupiter, but it was stuck. And for 2 or 3 weeks, our engineers were quite concerned. There was nothing they could do to get this arm to snap out. So they shook the spacecraft a bit. They turned the spacecraft to the sun to heat it up, which is a terrible thing to do with your 1.4 billion euro mission spacecraft. And wonderfully, they shook it loose. So what you can see here is it's on loop. You see the rime antenna coming loose. You see it snapping into place. It bounces a little bit and it locks. On the right-hand side, of course, we have the telemetry data, so the engineers could see that this worked. But actually having the movie, the picture speaks 1,000 words. So everybody was cheering in the control room at this point. So it's a beautiful solution to a technical problem. Now, I told you I'd tell you a little bit about the mission dynamics. This is important because we didn't have a rocket big enough on Earth to be able to launch directly to Jupiter. So we're going out into the distant solar system. Jupiter does have more gravity than a comet, and we need Jupiter to catch our spacecraft, but we need to get there with the right dynamics. And so what we actually have to do is we have to use some free green energy called gravity. And the way we do this is we've modeled very complicated flight dynamics and the engineering of our spacecraft and the mass of our propellant and all of these things together. And what we realized, we could do a gravity assist. So a bit like if you're swinging a ball on a string or a bucket of water, as you swing down at the bottom, you get a bit of a kick and it gets faster and faster, a bit like a swing. And so we realized we could do a double gravity assist between the moon and the Earth, never been done before, several of those around the Earth, and then you sling up to Venus, you do that again, and eventually you get all the way to the Jupiter system. We'll tour Jupiter, that will give us an extra bit of a kick, and then eventually we'll tour the moons, and we'll end up in orbit around Ganymede, which is the moon that we want to study in the greatest detail. Because the launch was so perfect, we saved some propellant in our energy tanks, fuel tanks, and we can do an extra orbit of Ganymede, and we can go closer to the surface than we'd hoped. We thought we could get to above 500 kilometers of the surface, but because of the beautiful launch, we'll now have enough energy, propellant left to go to just 200 kilometers above the surface of Ganymede, so that we will have exquisite views that no one has ever seen before. And we will get there in 2031, 2032. So many of you may be professionally working on the data when these come through. So you can see these are lifetime missions. I told you we had a flyby between the Earth and the Moon, and this is the movie that we took that was Flying by the Moon. And as I say, taking that energy from the ground to the sun, between the Earth and the Moon, very, very low and then as the movie continues on down, on the right-hand side, you can see some of so far. So our instruments work. We've found a habitable planet, so we know we can do this at Jupiter. But yeah, it's a beautiful, beautiful data set. So that's some of the coldest parts of the solar system. Harsh environments where everything has to work beautifully. And we've got a few years to make sure that our instruments do work there. But we're also going in the other direction, so into the inner solar system. Now that we know how to do these incredible flight dynamics, we're going to do something even more innovative at Venus. And this is a mission that we've just started to build. We've been given permission by our member states to put the contracts into industry and start to build this. And the idea of Envision is that we will study everything in our sister planet from the surface of the atmosphere down to the core of the planet. Now, what we actually have to do here, instead of trying to use the gravitational slingshot to pick up energy, what we have to do is we have to brake and get into orbit. So it's actually quite gravitationally difficult to get into the inner solar system. So we need to use some energy to get there. And then we have to slow down. And we need to get into the orbit. And we're going to do a thing called aerobraking. So we're going to use the antennas and the solar wings to literally kind of slow her down. A bit like when you're on a bike and it's going too fast and you put your feet on the ground to slow down. That's what we'll be doing. And then once we get into orbit, we'll be measuring all the properties of the atmosphere. So that's very exciting. It's a very hostile environment. It's very oxygen rich, and that tends to dissolve your spacecraft. So there's some materials science and some metal chemistry that our space engineers also have to take into account. So I don't like to boast, but we really like to do crazy, mad, difficult things. So an even more hostile environment than Venus is Mercury. Now, Mercury is small, it doesn't have so much gravity, but again, we're doing these flybys to slow down and get into the orbit of Mercury. It's also incredibly hot there. It's the closest planet to the sun. It's a bit like flying into a pizza oven. And we launched this in 2018, and since then we've been doing these incredible flybys to get closer and closer and closer to the planet. This was a swing by that we did in June 2022, and again we had some wonderful data. That's the surface of Mercury, and that's just a close-up view of the high-gain antenna. But the most exciting one we've done so far was on the 4th of September this year, where we skimmed to just 165 kilometers above the surface of the planet. That's the closest we'll approach the planet, because once we're in orbit, we'll be a bit higher. And in 2026, when we finally settle into orbit around Mercury, we will then launch 2 more spacecraft so that they can then study the planet. So you can see now that our missions not only have multiple instruments, but they have multiple spacecraft. So these are missions of missions, if you like. So that's going to be really exciting. Now, the reason that obviously Mercury is so hot is because it's very close to the sun. And we also like to fly in and study the sun. We have a number of solar missions, but the most exciting one recently has been Solar Orbiter. And we've been studying the sun in its normal quiet phase. At the moment, it's very active. That's why we see the aurora borealis. But the quiet sun is also important because the sun, of course, enables life on Earth. It also, if it does flare up, it causes problems for our spacecraft, for our built environment, potentially for our electricity system. And I love to put these together because the top left-hand corner, it's on a loop. That little dark splodge that's moving across is Mercury. So that's the terrible environment that Mercury is living in, with all of these solar prominences, radiation, energetic particles, and that's where our spacecraft are operating. I mean, it's crazy. Hands up if you're an engineer, or an engineering student, or... Oh, you guys are amazing. You have to be mad to want to do this stuff, right? And then you send the data back, and you have to fly it. Yeah. So anyway, I just want to show you that I think you're all amazing. And as I say, we have these incredible missions, and this is one that we're building. We like comets, so what we're now going to do, having learned how to do multiple spacecraft from Bepi Colombo, we're going to launch this in 2029. It's going to go with another mission, and it's going to go out into deep space, and it's just going to hang around. And it's going to look for a pristine comet, one that's never been in the solar system before, but that's come out from the edge of the solar system and will tell us about the origin of our solar system. We will then launch in space. So in deep space, we'll then launch the spacecraft from where it is. It will chase the comet, and it will launch 2 more probes to study the comet. Again, I think it's insane, but it's really, really exciting. And the big question we're trying to answer is, what's the solar system made of? What's its origin? And we think it might be twice as big as we ever imagined it to be before. So there's a lot of stuff out there. And sometimes when that stuff comes in to Earth, it can be a threat to our existence. We don't only study the planets in our own solar system, we study them across the cosmos, and we now have this incredible suite of missions. Cheops and Webb are flying and operating. Plato and Ariel are in development by the European Space Agency. Plato will study Earth-like planets around sun-like stars, so we're looking for our homes around other stars. And Ariel will study the chemistry of the atmosphere of 1,000 extrasolar planets. So we're now going to start to do climate change on other worlds, which I think is incredible. Now, that's the solar system, that's planets, and then, of course, the connection is to the rest of the universe. The other telescope that we launched in 2023 was Euclid, and this is an incredible mission. It's an M-class mission, so it's not one of our biggest, but it's absolutely transforming the way people do astrophysics. We have a whole new generation of astrophysicists coming through saying, wow, you broke how we did science. We now have to develop algorithms and do things in a completely different way. The big question that we really want to ask is about the origin of the universe, and in particular the dark universe. So the material that you and I and planets and stars and galaxies are made of, so-called baryonic matter, ordinary matter, makes up only 5% of the universe. The other 95% we don't know what it is. About 26, 27% of it is so-called dark matter. It gravitates, it pulls galaxies together, but it doesn't produce light, so we can't detect it with normal telescopes. And the rest is dark energy. We don't know what that is. But what we do know is that not only is the universe expanding, but that expansion is speeding up with time. And that goes beyond Einstein's laws of general relativity. So we have some unknown physics that we have yet to discover. So what Euclid will do is it will actually survey the universe for the next 6 years. The telescope itself is made of a very special material called silicon carbide. It's structurally very stiff and thermally very stable, which is what we need because we need very, very exquisitely sensitive cameras, and we don't want the infrared radiation from the telescope contaminating our optical and visible cameras. So we have a very clean environment. We discovered when we launched that we had a very thin layer of ice on the visible optics, so thin that it was thinner than a strand of DNA. But our cameras and our detectors are so sensitive that that dropped the light that we were able to see from galaxies. We've now decontaminated and heated up the inside of the telescope a little bit, and that ice is now defrosted, which is wonderful. We flew on a Falcon 9 telescope rocket from Cape Canaveral, and another beautiful launch. Clear blue skies. Kourou was a bit cloudy for Juice. Phenomenal launch. And as I say, we're going to survey the entire extragalactic sky back to 10 billion years in cosmic history. We can't do that by astronomers deciding each day which part of the sky to point at, so we will do this fully autonomously. We've already pre-designed the survey, and the spacecraft will do this in a very clever way to make sure that the scientists get the data that they need. So why is this mission special? Well, it's particularly special for 3 reasons. And usually any normal astronomy mission or ground-based telescope, you can choose 2 of these out of the 3. You can either have a wide field, you can have crystal clear vision and detailed resolution, you can have sensitivity. You can choose 2 of those. Euclid does all 3 because it's in space. That was a very special photograph taken by the Hubble Space Telescope. It was the deepest stare at the sky that Hubble had ever done. But Euclid now dwarfs that. So one single shot with our Euclid cameras covers an area 2.5 times the size of the full moon. Now, to display one of these images, I would have had to have asked our kind hosts for 64 4K by 4K TVs, which is not so bad, but keep that number in mind. And we released our first test images, if you like, or the first commissioning images back in November. This is one shot of the sky, and in here there's a heavy galaxy cluster of about 1,000 galaxies, and we have about 100,000 galaxies in this photograph. We have such great vision, though. We can also study the galaxies individually. This is a spiral galaxy like our own galaxy. This is a little dwarf galaxy. It's a collection of stars. These are the building blocks of the cosmos. And if we zoom in, still with the same data up here, we can actually study a little stellar nursery where stars are being born and they're blowing bubbles. And you can go onto our website, you can go onto our tool called ESA Sky, and you can just press the zoom button. I just sat for hours zooming and zooming and zooming. And the bright stars are in our own Milky Way galaxy, but a lot of these things are distant galaxies, so go find your own galaxies. And then, of course, we have our own stellar nurseries in our own Milky Way galaxy, and this is a beautiful image of the Horsehead Nebula. We released our next image, again to show the power of the telescope, a single shot, and I just literally pressed zoom on my computer here, and as you go in, you can see this massive group of galaxies, and there's a lot of hidden dark matter here. And what that dark matter does is it distorts space-time, and the light from distant galaxies, instead of being round galaxies or oval galaxies, the light gets twisted into these banana shapes. And so our scientists can actually measure the hidden mass and how it's distributed, the dark matter, based on the distortion of the background galaxies. And they want to do this ultimately for 8 billion galaxies. That's an awful lot of galaxies. So let me give you a sense of scale, because it's almost impossible to understand or to explain this. One shot of Euclid, 2.5 times the size of the full moon. I've shown you a few of those images and what it looks like when you zoom. Now I'm going to show you what we released a couple of weeks ago in Italy. We've now done a massive mosaic, 208 gigapixels. I would now need to have asked our kind organizers for 25,000 television screens to display this one image at native resolution. And what I would like to ask, if we could maybe have the lights dimmed, I'm going to take you on a zoom into this incredible mosaic. And remember that this is 100 million cosmic sources. There are 14 million galaxies in this patch alone that our cosmologists can start to measure the shape of. And this is only 1% of the final survey. is just the beginning of the work that our cosmologists will do over the next 6 years to try to unravel the mysteries of the universe. This blue haze is actually dust in our own Milky Way galaxy that when you look from the ground just creates a fog. But the crystal clear vision of Euclid means that we can peer through it and actually study the details of these galaxies and the very fine distortions of their shapes ultimately. It's a huge data processing challenge. We have 9 data centers, 8 across Europe, 1 in the United States, and eventually all of the data will come here to Spain, to ESAC, just outside Madrid. And again, it's huge collaboration and friendship. So 2,500 scientists working together, 2,000 industrial personnel. And I like to give this number, and some people like it, some people don't. We will study 8 billion galaxies. We'll pick the 1.5 best billion galaxies, and the mission cost was about 1.4 billion euros. So it's about 90 cents per galaxy. So less than the price of a cup of coffee. So I think it's not bad value for money. The next frontiers, of course, in terms of studying the dark universe is not with light and not with these sorts of stellar traces, but literally studying the nature of space-time itself. So we're now developing this incredible mission. My teams are going through a technical review today to pick the industrial prime contractor, so there'll be big news tomorrow, hopefully. This will be 3 spacecraft made identically. They will each have a test mass on them. They will fly on an Earth-Sun orbit, and they will be 2.5 million kilometers apart from one another. And they'll act as a single array. And so when ripples of space-time come past the spacecraft and the spacecraft wobble by less than the size of a proton, we'll measure those ripples and we will test Einstein's general theory of relativity. And this suite of telescopes will just orbit around the Earth, around the Sun on the same orbit that the Earth's on. So it's an incredible piece of collaboration again across Europe and out with our colleagues in the United States. And then finally, we're opening up a brand new window in the hot universe. So we think that almost half of that 5% of ordinary material is hotter than 1 million degrees, and we don't understand why. And we have to look at the highest energy X-rays. We have some collaborations with our Japanese and Chinese colleagues who launched 2 test missions this year who are really pathfinders for our next big European mission. GRISM is starting to measure in the X-ray the chemistry of elements in the universe in some of the hottest regions of space and looking to see how metals form. And then we're building a telescope that we hope we will have approval to start to really develop in 2026 called New Athena, which will be the biggest X-ray telescope in the world when we launch it in 2036. And again, huge European innovations and incredible materials that no one else in the world has been able to develop to take us into a completely new realm that normal optics doesn't allow us to do. So we innovate this technology across the whole of Europe. And whenever you start to develop new technology that works in a really extreme way, in new ways, in new places in the universe, as I say, you're then able to use those for other things, be that medical diagnostics. Some of our molecule sniffing technology on the Rosetta mission is now used in the perfume industry. So you can see the incredible places where the technology gets passed on to. And what for the future? Because I promised you that we needed a view to the future. So many of these missions are being developed. They'll fly in the late 2020s, early 2030s. But those missions were technologically imagined. The questions were asked many, many years ago in order to get them to the stage they are now. So we shouldn't stop if we want Europe to continue to lead the world. And if we want to give the next generation of scientists and engineers, like you in the audience, the opportunity to develop these technologies and to help to open up brand new discovery spaces for humanity. So we launched a call for proposals in 2019, and we had 100 science white papers come from scientists across Europe and collaborations around the world saying what ESA should do in the 2050s. And our expert team spent 2 years reading these proposals and ripping them apart and boiling them down to some main themes. And we've now decided that our next big L-class mission will build on the experience that we've developed to date, and we will go to the moons of a giant planet. We've had a 2-year technical and scientific study, and we've decided that we will go and do a tour of the Saturn system, and we will land, we will fly through the plumes of Enceladus, seek signs of life, not just habitability, and we will land on Enceladus. And we will look to see whether Enceladus actually has life on it. We won't do a sample return, that's beyond the scope of our budget, but we will have to be even more innovative because we will have to miniaturize our technology and make sure that we've built our labs in the spacecraft lander to act as a lab on the surface of Enceladus, which we don't yet know how to do. So this is our pencil drawing of what we think we'll need. We don't know what the launcher market will be then, so we're quite flexible. We will launch spacecraft and lander. We will do some in-orbit assembly above the surface of the Earth. As I say, we'll need 150 square meters of solar panels, much bigger than JUICE, which remember, JUICE are 85 square meters, bigger than anything, bigger than third generation Starlink satellite solar panels, because there's not much sunlight out at Saturn, and so we have to catch every ray of sunshine. And we already have our deadline. So in 2052, the south pole of Enceladus will be illuminated by the sun. So we must land in 2052. In order to land in 2052, we need to launch from Earth in 2043, because that's how long it takes to get there and do the tour. We know that from Jupiter. And in order to be able to be ready to launch, to build the spacecraft, to miniaturize all the technology, to be absolutely ready, not test technology, but proper technology, we actually have to have matured our technologies and have our mission approved to build in 2034. So I can already book my approval committees in the calendar. So next year we will go to our Council of Ministers, our 22 countries, and we will say, could you increase our budget a little bit? Not a lot, just a little bit, and sustain it all the way to 2031 so that we can give the next generation the mission that makes your eyes water. And we have lots of work to do at pace, new technologies, new talent, next generation industries. I hope we inspire you. We invite many school children to ESAC. We run education programs. We work with teachers from around the world. We also have an ESA Space Science Fellowship program. So if you have your PhD, you can apply to come and work at ESA in any of our establishments or more than one through the course of the fellowship. And the idea is that you learn how ESA works, you bring your independent ideas, you win it through open competition, and then you become a space leader in the future for Europe. The data that we gather from our missions after a certain period are all publicly available, and we're constantly building new software tools to make these databases available to new communities. So I had one young woman who came as a research fellow, and she said, I think I could use your Planck cosmology satellite, which measured the dying embers of the Big Bang, to find all the metal asteroids. Who knew? Wonderful. And she's now doing that. We find the metal asteroids, we could go mine them. And of course, the public are hugely interested in what we do. We kind of get free advertising. You do something as incredible as Euclid, the newspapers want to write about it. And the media, there's lots to talk about in the world at the moment. There's lots of conflict, there's lots of war, there are terrible news stories all the time, there are elections everywhere. And in fact, even the space news is very, very busy. So to actually get on the front page of newspapers like the Metro is a huge achievement. And that really shows the power of friendship and collaboration when we try to do something together for the good of humanity. So at ESA, we're delivering our Director General's Agenda 2025, which is about increasing those talent pipelines, increasing the diversity of people who work in the European space sector. We're developing a strategy for 2040, and you can see for the missions that I have the privilege of leading, 2040 is really soon, it's not that far away. Voyage 2050 has already been laid down. And so we're just really keen to start. I hope our ministers will be kind to us next year. If you meet any of your ministers and you like the talk, have a little word and say, I think you should put some money in there because the future starts now. Muchísimas gracias. And I'm very sorry I was a little bit over time. If there are questions and you have time, I'm happy to take them, or otherwise we can do them offline.
Can you hear me? Yeah.
Yeah.
First of all, thank you for such an insightful presentation. It was really interesting. And I have a question regarding the image from the Euclid Space Telescope. Would you happen to know why this strange shape, kind of
The holes?
sweet potato, and the gaps in the image?
Yeah. So when I showed you how the telescope surveys the sky, it's an autonomous survey pattern. So at the end of the 6 years, all of those gaps will be filled. But what we have to do is we have to make sure that we don't overscan one part of the sky and go too deep and another bit gets missed. And so we have a very special sequence to complete the whole lot. This is just 1% of the survey, remember. And obviously for public consumption, we also had to make sure that everything was calibrated. So those bits will get filled eventually. We do have some parts of the sky where we'll do deep fields because we'll do extra science there. And then when I said we're covering 36% of the sky, the rest of the sky is filled with the Milky Way. And we've already done the Milky Way because we did that with our Gaia mission. And that's what the other 64% of the sky looks like. And each of the points in here, this isn't just light, each of the points in here is a star. We've measured the position, the brightness, and the properties of the stars, where they're coming from, where they're going to, and ultimately what the origin of the Milky Way is. And because we live about 2/3, the Milky Way supermassive black hole is here, and we live about 2/3 of the way out from the met center of the Milky Way. So when we look at the sky, you see that patch across the sky. So going out to L2 and flying around, we avoid the light from the Milky Way. The zodiacal light, which is the sunlight scattered off dust in our solar system. And then we look at the other parts, the other 36% of the sky, which is the rest of the universe to 10 billion light years. Thank you.
Thank you, Carol, for your presentation. And I was wondering, as I was watching your presentation, that if ESA has some focus into developing technologies and developing science to improve the habitability of humans in space or in other planets. I was wondering that.
We
There are any
do.
programs?
So we have a number of directorates. So I cover, if you like, big science. The Directorate of Human and Robotic Exploration, my colleague Daniel Neuschwand is director of that. So that covers our astronaut program. And so, of course, we have our training center in Cologne. So there we do a lot on human health, on astronaut health. We obviously care about the sun and the particles and the radiation that comes from the sun because that impacts astronauts' health when they're working in the International Space Station or ultimately if they're on a lunar or a Martian base. We also study their health when they're in space working on the space station because we know that you lose bone density, you lose muscle tone, and so we don't yet know how to fly humans safely to Mars to live there and come back. So there's a lot of research that goes on to human health, and of course it has huge impact back for patients on Earth. So, many of our elderly population might suffer from osteoporosis, and it's very similar to having been an astronaut in the space station for a year. So there's lots of dual-use science there for good on Earth. And also, I think once you've lived and worked on the space station and you look down at the Earth, every astronaut you speak to says, gosh, we have to protect this planet, this thin atmosphere that protects us. Mars doesn't have much of an atmosphere, Moon doesn't have one at all. So there's something about caring for our home, and maybe when we're in our everyday lives and we're stuck in a traffic jam or something, we're a bit grumpy, but my goodness me, when you get that view, you come back and you start thinking we have to protect what we have. And I think in the future, we see, lunar resources or maybe mining asteroids. There are ideas about developing technologies for doing the kind of the dirty bits of mining processing off-world because we actually damage our own planet by doing these things. So if there's a way to use space in a way that makes our own planet more habitable, then that's certainly something we're very keen to develop. So thank you for your question. Thank you.